Yay!
Yay! Hey, here's sort of a neat connection between the microscopic world and the macroscopic world. So what I mean is, I've seen this example a number of different places, is connecting the orbit of the electron, which we can think of as a little current loop, to magnetism and how magnets work. Because if all magnetic fields come from currents, how do like refrigerator magnets and permanent magnets work? Because you don't plug them in or anything. Well, one possibility, one thing that you could imagine is that maybe the electron spinning around the nucleus acts as a little current loop, and maybe that's where the magnetic field comes from. So just to play with the idea a little bit, take the simplest model, the simplest atom you can think of, like hydrogen, and just imagine the electron circling the proton. And we've done this before. So what we said was, if we imagine that the electron is like a classical particle, it's not at all clear that we can do it, but let's just do it anyway. What we said was just apply Newton's laws to it, Newton's second law. So the electron, the force on the electron is Coulomb's law, right? So it's Ke squared over the distance squared. That's the attraction between the proton and the electron. And this has to equal, if that's the only force on it, this has to equal how it's accelerating, right? The mass times v squared over r. There we go. So that's just centripetal acceleration. And if we do that, we can kind of arrive at an expression for v. So v turns out to be, let's see, what's it going to be? Ke squared over mr. There we go. And if you plug those numbers in, what you find out is that v is way less than the speed of light, less than 1% of the speed of light. So if you're worried that, oh no, we have to treat the electron as a relativistic thing, we're going to be okay. That's not true. So maybe this is going to be all right. And then what we said before was, if you want to imagine that this is a current loop, I can kind of compute a current. The current, due to this thing, is like the amount of charge that goes by in a certain amount of time. So what charge just imagine one orbit. One charge of the electron's worth is going around in one period of the orbit. What's a period of the orbit? Well, it's going to be the distance this thing travels, 2 pi r, divided by v. Right? Distance divided by speed is going to get you a time on the bottom. So that's just going to be, it looks like ev over 2 pi r. And maybe that's going to be kind of a mess. I don't know. Let's see. So the current is just going to be E over 2 pi r times this mess, Ke squared over mr. That's kind of a mess. But anyway, let's see what we can do with this. If this is a little current loop, one thing we can do is we can compute its magnetic moment, which is sort of like the strength of the magnetic field coming from this thing. And the magnetic moment is just the amount of current times the area. So let's see what we get. This is going to be E over 2 pi r, and then I got this business Ke squared over mr times, what's the area of this thing? It's just going to be pi r squared, right? So what do we come out with? We're going to have, if I bring r squared, I'm going to have a k. Looks like I got a k. If I bring the e inside, I square it, right? So that's going to be like a k e to the fourth. If I bring the 2 inside, that's going to be a 4. And the pi, well, the pi's are going to cancel, thank goodness, so I don't have to worry about those. In the r, so I'm going to have in the bottom, I'm going to have a 4. I still got my m. What do I do with all the r's? Let's see. The r squared cancels with the r on the bottom. I just got 1 r on top. And if I bring that inside, this is just going to be an r up top in the square root. Right? So I've got this. Well, the neat thing is that this is all more or less fundamental quantities, right? That K at the beginning, that's our Coulomb K, 1 over 4 pi epsilon naught. Those are just fundamental constants. E is charge of the electron. R was, what's that? That's the distance. Oops, R. That's terrible. Make that a little bit better. So this distance is just going to be R. That turns out to be something called the Bohr radius, right? The smallest, the minimum distance of an electron from a proton. So it's a pseudo fundamental quantity. So anyway, that's the R, and then M's the mass of the electron. So those are all fundamental things. So this is some sort of a fundamentally smallest magnetic moment. So let's see what we're going to get out of this. If you plug in all the numbers, what you get is about 9.3 times 10 to the minus 23 in magnetic flux units. I won't bother putting the units on there, but so this is about 10 to the minus 20. Oops, sorry. Get these things mixed up. If you plug your numbers in, you get about 10 to the minus 24, which is about 10 to the minus 23 in magnetic flux units. And this has a special name. This is called the Bohr Magneton. So it's sort of like the smallest possible magnetic moment. You can't think of one smaller than that because you got a fundamental charge and a small distance away from a nucleus. So that's kind of cool. So how this relates to magnetism is, imagine that I have a whole bunch of these. Like a magnet is composed of a whole bunch of atoms that all have this kind of a setup. And if this is the smallest possible one, let's just for the simplest toy model, suppose that each atom has one of these things. What you can imagine is that normally atoms have a bunch of electrons that are in pairs, and these paired electrons, one might be spinning one way, one spinning another way, or in three-dimensional space, they sort of all cancel each other out. But maybe some atoms have unpaired electrons, so that this is important for one of the electrons. So just to keep the model simple, suppose we have one of these per atom. If I have, this would predict for about 100-gram magnet, the molecular weight, the molar mass of iron is like 56, something like that. So if I have something like 100 grams, that's about 2 moles of iron, right? Just happen to have something like that. So if I have a disk or a cylindrical magnet, this thing weighs a little bit over 100 grams. If this were iron, it's not. It's like neodymium or whatever. But anyway, just for the model, suppose this was an iron magnet. It would have something like 2 moles of iron in it. And if it's got 2 moles of iron and each one is contributing that much magnetic field, what would be the total? Would be the strongest magnetic field that such a magnet could possibly have. This would be about 2 moles. 2 moles of iron. Oops. The total magnetic moment is just going to be, what, 2 moles? So it's going to be 2 times 6 times 10 to the 23rd atoms are in each mole. And each atom is going to give you, this is atoms per mole, just to show how the units cancel out. And then you multiply by, let's see, that gives us a total number of atoms, right? And each atom gives us the Bohr magneton up there. Each one gives us a little bit of a magnetic field times 10 to the minus 23. Well, the nice thing is those things cancel right out, right? So we get something like 12. So the total magnetic moment is 12, and I just happened to look up what the magnetic moment of that magnet was from the manufacturer, and the true number is like 13.3. right? So that's kind of cool that it doesn't mean that this is exactly what's happening, but it just means that it's at least consistent, right? This story could possibly be true. It turns out, if you know this already, it turns out it's kind of not true, but it's like half true. Let's go back and look at, because there's something else that's kind of cool about this. If this is the smallest possible mu, let's look at it in terms of something from physics 1, which is like angular momentum. So let's go back and look at this. I was EV over 2 pi r, right? I had something like that. So let's look at this mu. We had, let's do it over here. Mu was equal to I times A, and we said that that was EV over 2 pi r times pi r squared. Well, the pi's go away. Let's not plug in the v. Let's just look at it with the v in there like this. So this is just going to be EVR over 2. All right. What you might notice is that thing, that the r times v, that's starting to look a little bit like an angular momentum. In fact, it'll look a lot like an angular momentum. Remember, the angular momentum of a particle traveling around the circle is mvr, right? The magnitude of the angular momentum traveling around the circle. Well, I've almost got that. If I multiplied the top and the bottom by m, then I've got it on the top, right? So this is going to be E over 2m times L, the angular momentum. And in fact, this ratio between the magnetic moment and the angular momentum is something called the Gyromagnetic Ratio. It becomes a little bit more important in particle physics, but that's a neat kind of a fundamental quantity. The cool thing is that little L, that's sort of like a smallest possible angular momentum in the atomic realm, right? It's an electron as close to the nucleus as possible, and it always travels at sort of that fixed speed v. So that's kind of a special tiny angular momentum, a special tiny unit of angular momentum. Let's see what it is. L is mvr, right? So that's going to be mr times our v. Let's plug in the v that we had earlier. So that's going to be k e squared over mr. Let's see, so I can write this as, if I bring the m in there, that's going to give me a square root of m on the top. That's going to give me an r on the top and a k and an e squared. So what this turns out to be is about 1 times 10 to the minus 34th. And this is a really special quantity. It's the smallest possible angular momentum in some sort of atomic sense. And this is given a special name, h bar. This is Planck's constant, h being Planck's constant. H bar is actually Planck's constant divided by 2 pi. But anyway, this is given a special name, 10 to the minus 34th. It's the smallest possible, it's a unit of angular momentum on the atomic realm. And so this is sort of a peek into quantum mechanics and the atomic realm. Maybe this is responsible for, maybe quantum mechanics ultimately is responsible for magnetism. And it turns out they're very closely related. This is almost the right story. The only difficulty is what really happens is that it's not so much the orbital angular momentum of the electrons that matter as much as the spin of the electrons. The electrons spin around their own axes. And so in that sense, it's like a really, really teeny tiny current loop. And the annoying thing is that now the value of the electron spin is not h bar, it's half. These are called spin half particles. And so the fundamental unit is h bar over 2. But it's neat that it still comes as just a simple multiple of the smallest angular momentum, h bar. So electrons have a spin around their own axes that's half of their orbital angular momentum, and this is what ultimately is really responsible for magnetism. So that's kind of a cool connection.